Nice to see you. We can start, and we proceed to one of the principal structures of our course, which we will use. It is the Poisson structure. I suppose that most of you knows very well this structure, but we will repeat and make necessary remarks and accents related to this structure. So the title is Poisson Structure, and we will start by a very close notion, which is called Hamiltonian dynamics. Dynamics. And we will discuss it firstly in the simplest case. We will consider the space R to n with a special choice of coordinates P1, Pn, Q1, Qn, as just the coordinates on this two n-dimensional space. And we choose a function m and define a system of differential equations with respect to some time t, p I dot. So it's the derivative with respect to time. It is equal minus dh over dqi, and qi dot is equal dh minus dpi. So this dynamical system, this system of differential equation, is called Hamiltonian dynamical system on this space with this choice of variables corresponding to the Hamiltonian function h. So I suppose it is known as an example of such system. Example. I'd like to choose n equal 1. So it is m. It is just a two-dimensional affine space, and the Hamiltonian function is such p square plus alpha q square. The Hamiltonian dynamics corresponding to such a function is the following one. So q dot, it is just p. So p in this notation is just the momenta, the velocity of the coordinate q, and p dot is minus maybe it's better alpha square over 2. I prefer this this normalization. And p dot is equal to minus alpha 2q, because here there is minus, and it produces an equation of motion with respect to only the coordinate q, the second derivative with respect to time, d square q dt square is equal minus alpha 2q. So it's a linear differential equation. We all know how to solve it, but I like to write it down. So q depending on t is equal A cosine of alpha t plus b sine of alpha t. So this motion, it is called harmonic oscillator, and it represents some oscillating object. Those coordinates and momenta related by this formula, and coordinate is just some oscillating process. Okay, but now we will define the same equation by introducing some new operation on the algebra of function on the variety M. In our case, the variety is just the affine space, but I'd like you to take in mind the generalization. So during the course of differential geometry, you will work with more general varieties, and most of the explained structure exists on general manifolds. So, but first of all, I'd like to define the Poisson structure on the standard Poisson variety definition. We define an operation on a pair of function which will be the following expression: df dpi multiplied by dg over dqi, the sum minus the reversed derivatives, qi dg over dpi. This is an operation which sends a pair of function. I'd like to write here the tensor product of modules over C. Over our field R. And it sends it to the same ring or the same algebra. And what can we say about it? So it is obviously, so this symbol means that it is bilinear over the field of reals. So it's bilinear linear over R. It is skew-symmetric. 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 It satisfies the Leibniz rule. So f g multiplied by h, it is the same as f g multiplied by h plus g f and in the Poisson bracket of f and h, and the same for the first argument. It is the consequence of the skew symmetry of this operation. And maybe the most important and structural condition of this operation, it is the Jacobi identity, which we know from the definition of a Lie algebra. G H F plus H F G equal 0. Jacobi identity. let us see which properties are evident and which demand some demonstration. So the property of being bilinear, so we can multiply functions by constants. So it is clear that the derivation is a linear operation with respect to multiplication by constants. It is not the same if you multiply by a function, but if you multiply by constants, it is bilinear. So this is trivial, the bilinearity. The skew-symmetry, it is due to this minus here. So if we change arguments f and g, we just exchange two summand in this sum. So and the minus here, the sign minus implies this skew-symmetry property. Fg is equal minus gf. The Leibniz identity. Leibniz identity. Do you need some evidences, or is clear? So it's an effect of the derivation operations here. So it is defined. This bracket is defined by derivation operation, and this derivation operation satisfies the Leibniz rule. So the Poisson bracket itself do. And how to demonstrate the Jacobi identity, please. The simplest way to see that it is true on linear functions. Demonstration of the Jacobi identity. Jacobi identity. Let's see this identity on linear functions. What does it mean? in place of f, g, h, I should put just the coordinates, some coordinates p or q. F, g, and h are some pi or qj in all possible choices. But if we see carefully this expression, if all functions here are linear, then the first bracket here gives a constant. And the Poisson bracket of each function with a constant is 0, because it is defined by differentiation. Okay? So if you place, if you take f, g, h as some linear functions, then it is 0 just by trivial observation, that just each summand in this identity is 0. But when we should use the Leibniz rule, so if, for example, if this is true for functions f, Jacobi identity fulfills for f, g, h1 and f, G and H2, then the same is true for them fills for F, G, and H1 multiplied by H2. Why it is true? Because substituting here the product of H and expanding it here, so it's better to write it down. So F G H1 multiplied by H2 plus G H1 multiplied by H2 F plus H1 multiplied by H2 F G. It is equal, here by the Leibniz rule, F multiplied by the Poisson bracket of F with G H1 multiplied by H2 plus F G H2 multiplied by H1 okay, plus G H1 F multiplied by H2 plus G H2 F multiplied by H1 H1 F G H2 plus H1 H2 Fg. When we should apply the same rule here, let us see. It is F H1 multiplied by H2 plus F H2 multiplied by G H1. So it's not so evident, but let us finish this calculation. G H2 H1 plus F H1 G H2 G H1 F H2 plus G H2 H1 F plus G H2 F multiplied by H1 plus G H1 multiplied by H2 F, and I need more place, plus H1, it is already done, H2 plus H1 H2 Fg. There are some so here, let us consider here this term, and this term. Altogether, they give the Jacobi identity for the functions f g h1 multiplied by h2. Okay. Fg h1 g h1 f and H1 FG. So it's the Jacobi identity for the set of this set of functions Fg and H1. So it is equal to 0. It is multiplied by H2, but it is not dramatic. The second group, FGH2, multiplied by H1, GH2F, and H2FG. So this group of summand is trivial by the same reason. So it is the Jacobi identity for the set of functions f, g, and h2 multiplied by h1. H1, But these terms cancel each other due to the skew symmetry of the Poisson bracket. So it is GH1, but here is H2F, and here is FH2. Okay. And it should be the same in this case. So it is FH1, and here is H1F, and GH2, GH2. So this Jacobi identity, you see it is in some way graded. So if you can prove it for lower functions, for linear ones, you can do it for all functions.
What do we do here? I mean, for what we just checked some Jacobi identity?
I checked the Jacobi identity for the simplest example of Poisson structure, which is the standard Poisson structure on R to N. But I prefer to demonstrate this technique. It represents the algebraic properties of the Poisson structure. So you see, if you can prove it for linear functions, then it is true for all functions. Just a problem for you. Task. Let's suppose we have Rn and an operation with coordinates x1, xn coordinates. And we define the structure like this: xi, xj. It is just Cij, xi, xj. And Cij, it is a skew-symmetric valued matrix. So the statement is that it is always defines a Poisson structure. So the Jacobi identity is always fulfilled. There's no other demands. Understand? Always defines a Poisson structure which means that the Jacobi identity fulfills. How to demonstrate this? So it's a task for you, but the idea is the same, that you should verify this identity for some simple functions, but they are not linear in this case. There are some other good choice of functions for which it is simpler to verify the Jacobi identity. Okay. And we proceed to more general definition to the Poisson structure, which we see in this example. A general Poisson structure on the manifold M, but now we suppose that it is just R and in what follows you will use a more general definition, but for the moment we suppose that it is just a affine space. A general Poisson structure is an operation also on functions, on smooth functions, given by the formula f and g is equal to the sum p ij df dxi j dxj such that it is skew-symmetric. Skew-symmetric means that fg is equal minus gf. The Leibniz rule is fulfilled automatically just because we have written this in terms of some differentiation operators. And pi j are some functions on M, not necessarily constant, as in the case of the standard Poisson structure. So it is skew-symmetric. The Leibniz rule is just a consequence of this form, and we ask to satisfy the Jacobi identity. Jacobi identity. B identity. Example. If n is equal to m, and we consider just this standard Poisson space, Poisson variety, and the standard Poisson bracket, which is the sum df dpi dg dqi minus df dqi dpi. So comparing to such expression, we see that all pi ij are some constants.
Yes.
Okay, one here, then the indices here coincide, and minus in the second summand. It is very convenient to express pi as a matrix. In this case of the even dimension of our space, we can divide our space into parts, part of coordinate pi and part of the coordinate q. So here is pi 1, pi n, q1, qn. Here pi n, q. I'm sorry, m, q1, qm. And pi in this case is 0, 0, 1, minus 1. Okay? So in this case, the bivector is given by this matrix. It is skew-symmetric. It is necessary for this condition. And it is very simple. So it contains only unities and minus unities on the diagonal of this matrix. Is it clear? Okay. Just one moment. Poisson structure on M it is the same as the following structure. The Lie algebra structure on Cm. You see that the Poisson structure defined here is just a way to make the space of function a Lie algebra. Okay. So it's a Lie algebra structure on C infinity M, but which is related very strongly with the ring structure on this space. So we can multiply functions. So on this space there is a multiplication operation, just a commutative multiplication of functions. An additional operation which is the commutator, which put the space to the algebra. So there are two structures, and it is very important when we can quantize the classical phase space. So both these structures start to make a part of the non-commutative multiplication on the space of quantum observables on the same space. You see, they're not, they're very coherent. They're related, and they are related by the, not by the Jacobi identity, but by the Leibniz rule. So their relation, the relation between these two structures is the Leibniz rule. And it is very important to construct a quantization. So it is the Lie algebra on the structure, on the space, compatible with the ring structure on the same space. The ring, I prefer to say with the commutative algebra structure, with the commutative algebra structure on the same space, space C infinity, through the Leibniz rule. Leibniz rule. So we will think now about this this space is a space with two structures which are compatible. And so it was the idea of Sophus Lie at his time to introduce some algebraic structure into the field of dynamical systems. So he invited Lie algebras to study dynamics. And we will see how it works. So using some technique from the Lie algebras and Lie groups, we can construct, for example, dynamical systems which prescribed properties with some controlled properties about the behavior of this system. Okay. Let us return to the definition. So I have just defined that we need such properties. But if pi are some functions on M, it is not quite evidently how to guarantee the Jacobi identity. So now we will prove some theorem. pi ij satisfies the Jacobi identity if and only if the following is true. Pi ik d pi l j k over dxl plus pi jl d pi ki over dxl pi kl d pi ij over dxl and the sum over L is equal to 0. Let us.
This is the Jacobi identity for this pi?
Yes, but we suppose that pi is skew-symmetric. So it is necessary here. So we suppose that there is some bivector. It's a matrix, so it's a bivector. It is true bivector in tensor notations, but you need some notions from the theory of smooth varieties to pronounce it in some reasonable way. But we need this bivector to be skew-symmetric, and if we choose some bivector which is skew-symmetric, then it satisfies the Jacobi identity if and only if this condition fulfills. Let us see that it is always true if this bivector is constant, has constant values, okay? Like the standard bivector for the standard Poisson structure. Because there are derivatives here, they all will be 0. So it is true for some evident choices. But in the case of task, which is your home task, it is not so evident. Okay, I will make some calculation. Which is just straightforward. So we have to write the Poisson bracket FGH of 3 functions in different orders h f plus h f g. So by definition here, it is p ij. I will pil df dxl dxi, I'm sorry, d gh. So I will do some preparatory calculation over dxl, and this is the following thing: il df dxi, and now I make the second derivative dxl to pi jk dg xj dh dxk. And this is the same as df dxi. Here are three derivatives. The first one is d pi jk dxl dg dxj dh dxk. And there are other two derivatives, pi il pi jk df dxi d2j d2g dx j dxl dh dxk, and plus pi il pi jk df dxi, and here I should take the second derivative of h, dg dxj d2h dxk dxl. Okay?
Isn't there really some?
Yes, there are sums over L. Over L. There is a sum over L, yes. Other indices are, and here there is the sum over J and over K. Yes, yes. So I use the Einstein rule to sum over a pair of indices, one of which is up and other is lower. Okay. So there is sum over I, sum over L, sum over J, and over K in all these expressions. Okay, you see that there are expressions of two kinds, and this expression is very close to which I mentioned in this condition. So it is this expression multiplied by some derivatives of functions. Okay. I'd like the simplest way is to write down all these expressions. So now I will write this expression, and it takes the following form: pi jl by jl df dxj d pi. Here is the pi of ki over dxl df. I'm sorry. dh over dxk df. I'm sorry. Here is g dxi. I will write it, and we will discuss why it is written in such a way. Pi jl dg over dxj pi ki d2h over dxk dxl df dxi, and plus pi jl dg over dxj pki dh over dxk d2f dxi dxl. So this is the second term in this equality. So the principal hint in this calculation, it is to relate the indices of this summation with the functions. So all the differentiations of g is over xj in this form and in this form too. All differentiation of f are over dxi. So it is the choice of indices, just to sum well the similar terms in different sums. Okay? And then the third term is similar, so it's pi. But firstly, I differentiate h, and h I always differentiate over xk, kl dh over dxk, d pi ij over dxl, df over dxi, dg over dxj. Okay? Then pi kl dh over dxk, pi ij, and then the second derivatives of f and g, xi, xl, dg over dxj, and plus pi kl dh dxk, pi ij df xi, d2g dxj dxl. All first terms in three sums. It is this identity. The Jacobi identity is always sum, all sum, yes. But these three terms, let us break it. So the three indices here are I, j, and k. I, j, and k. L, and we consider the sum over L. Okay? So is equal the sum over L is B I, j, k multiplied by df over dxi, dg over dxj, dh over dxk, sum over I, j, and k. But this term is very important. It is called this Schouten bracket. This one. It is the Schouten bracket of the bivector with itself. It appears in modern concept of deformation quantization in quantum mechanics, quantum field theory. So very useful, very good abstract way to define Poisson structures. Okay, but do you agree with this formula? So in all these terms, there are first derivatives of functions, and they are multiplied by some expression in which there are pi and derivatives of pi, first derivatives of pi. Okay. I'd like to say the following thing, that the sum of rectangular parts of our expression is 0 for all values of f, g, and h, if and only if these coefficients are 0. Okay? Because it should be 0 for all f, g, h. And we can place here, for example, just the linear functions, and we can obtain all coefficients here. And for all choices of linear functions, it should be 0. That's why all coefficients at all monomials like this, should be 0. But, okay, now I should understand how other terms cancel each other. For example, the term with the second derivative of h. It is here, and it is the second derivative of h.
I think due to antisymmetric structure, maybe they will cancel.
And here, yeah.
Which one? Ki, and here jk.
Yes, the coefficient with this term. So what I'd like to erase something. Okay, you see, the functional coefficients is d dg dxj df over dxi and d2h over dxk dxl, and the coefficient it is pi jl pi ki plus pi il and pi jk. So here there is a sum of all these terms
Sum
over I, j, k, and l. Okay, but I'd like to consider two terms in this sum. For all I, j with k, l and I, j, l, k. They are both presented in this sum. Okay? I'd like to see that for each I and j, this exchange of k and l cancel this sum. So this is not changed if we change k and l. But what happens here? I, j, k, pi l I plus pi I k and pi j l. Okay? If we change k and l, there is a term of this type in the same summation.
So you're allowed to change it because you have sum over all four indices, right?
And because the second derivative is symmetric with respect to this change.
Yeah, yes.
So they have the same part here if we change k and l.
Yes, okay.
Okay? What happens here? So this term is the same term as this one, but is the exchange of indices L and I. Okay? So these terms cancel each other. Because pi is Skew-Symmetric.
Yeah, but from the upper line you get the lower line, right? No.
Both lines are present in this summation. But I see two such parts of the big summation. For the same I and j, but for the exchanged k and l. They are both present here. And my statement is that they cancel each other. This cancel, I'd like to write it. And here I change dxl, dxk. But these parts are the same.
Yes, yes.
Because the second derivative is symmetric.
Yeah, but now you have to cancel the other two.
Yes, because the bivector is skew-symmetric. And this one, so
Also, yes, cancel out.
this coincide and this one has inverse signs. Okay? And it is the same for other coordinates.
So everything is proved.
Yeah. So all terms with second derivatives cancel each other, and the equality for the squared parts is equivalent to the vanishing of all these coefficients. And these coefficients so are given by these expressions and are called the coordinates of this Schouten square of the bivector with itself.
So the other two derivatives was also there.
Sorry?
So the other two derivatives are also there.
Yes, yes, yes. It is the same calculation. Okay.
So it's important to put the indices correctly.
Absolutely. So just some notation. We will notations. We will denote a bivector the following expression: pi ij d over dxi d over dxj. Okay. So it is a differential operator acting on a pair of functions. That's why it is called a bivector. So it's not. There are two terms of this expression. So we will call such an expression Poisson bivector. Bivector. And it is Houghton bracket. It will be a three vector, which is ijk d over dxi. I'd like to write down here the wedge symbol xj and d over dxk. Sorry, and it is much better to write indices, write upper indices here. I'm sorry, ijk. So there is some operation on vectors and bivectors, which is called this Houghton bracket, which is calculated in our case by this expression. But so ideologically,
is this like exterior?
Exterior product, yes. Exterior product. So it is an element of the third wedge power of the tangent.
I don't understand from where this comes.
For the moment, we can't go through the details, but all what is written is correct, and I want you to make the connection with what will follow. So this condition for a bivector to define the Poisson structure is equivalent to this beautiful condition that some element have the zero square.
Yeah. It's not commutator.
It's a Houghton commutator. It is not zero for each bivector, but the condition to satisfy the Jacobi identity is equivalent to some well-defined commutator of bivectors with bivectors. Very important example of the Poisson structure, which will play a crucial role in our course. Poisson-Lie-Kirillov-Souriau structure. Souriau structure. But in different textbooks, there are different names for the structure. So we should take Lie algebra and what is called the symmetric tensor algebra of Lie algebra. Do you have an idea of what is it? Symmetric tensor algebra or the vector space. No. So let our G be GLN R. It means that it is generated by the letters E, I, J, just the matrix unities. with a natural commutator KL, which is EIL delta JK minus EKJ delta EL. Okay? It is the commutator in matrices, just n by n matrices. Now I want to consider the algebra of polynomials in letters EIJ. Okay? It means that I can write E1, 2 square multiplied by 1, 3, E2, 3, something like this. And the sum of monomials of this type. Okay? Just the commutative polynomials. So this ring, it is a commutative algebra. We can multiply polynomials. Okay? But we can define the Poisson structure on this space. It's the Poisson-Lie-Kirillov-Souriau structure on this space. How it works? It is defined as a commutator in a Lie algebra on linear function, as a commutator on G on linear monomials. What does it mean? It means that Eij, Ekl, the Poisson bracket of these functions, because they're functions, they're some polynomials. There are some polynomials. on the dual space. Okay? Just the generators are linear functions on the dual space. And then if we consider all polynomials, they're just all polynomials on the dual space. Okay? So we consider the ring of polynomial functions on the dual space. And how we define the Poisson structure? There are linear functions on the dual space, which are just the generators of the Lie algebra. Okay? And we define the Poisson structure on such functions, just as a commutator in the Lie algebra. Okay? So this commutator is also a linear function, just the sum of two linear functions. And then we extend this definition by the Leibniz rule to all polynomials, on linear polynomials, and extend it to all polynomials by the Leibniz rule. For example, if n is equal to, it means that we have just a Lie algebra of matrices 2 by 2. GL 2R. There are 4 generators, 1, 1, E1, 2, E2, 1, E2, 2, E1, 1 with E1, 2. Do you know?
So there would be like a structure constant, and then the constant will be
just this commutator.
okay.
e to 1.
Yes, it is.
Yeah, only this term works.
Minus
Yes.
to 1.
Yeah. Minus e to 1. E11 with ey1, I don't write it. Okay. But e11 with e22. Zero. What E12 with E21? Okay, it's E11 minus E22. And what else? E22 with E12. It is minus E12 and E22, E21. It is E21. Okay. And the definition for the Poisson bracket of these generators with themselves should be the same. So, for example, E11 with E12, it is E12. But now we have to extend it to all polynomials. For example, we have to calculate E12 square, E12 with E21. What is the Poisson bracket? How to calculate? By the Leibniz rule. By the Leibniz rule. So it is equal to 2 A11 E12 with A11 E21. It is the Poisson bracket of this with this. Okay. Plus E11 square and E12 E21. This is minus E21 minus 2 E11 E12 E21, and this is E11 plus and minus E11 square E22. Okay. Do you understand why they will don't meet some obstacles? So why can we define the Poisson structure of all polynomials? Okay, it will be the good question, but it is a definition. We will work with it. And now we'll discuss another notion, symplectic structure. I need some words about differential forms on smooth varieties. It will be described in details through the course of Evgeny Vadimovich on differential geometry. But I need some definition. I will give you this definition in coordinate. So we consider an example of a smooth variety, which is just Rn with coordinates x, 1, xn coordinates. 0 form on smooth varieties, 0 differential forms. forms are just smooth functions. Functions. It means that just a function. So 0, just C on M. And there is an operation on smooth function which is called differential of a function, and it is written in coordinate like this: df dxi dxi, also the sum over I. At this moment, I propose to see it just some formal expression. One forms.
It was like one form.
Yes, it's a one form, but general one form on Rn. It is the following expression. It is the sum of d. I'm sorry. Fi d xi. Else, I suppose, a summation over I. Here is the upper index, and here is the lower index. And this expression df is obviously an expression of this type, but with functions here which are produced from one common function. So these fi in this expression are just the derivatives of some one of a function f. So it's an element of the space of one forms, and there is also a differential defined on one forms which produces a two form. So a differential. I will call this object lambda. The space of such object is the space of one forms, and the lambda is the following. dfi over dxj, and here dxj dxi. Here is the summation of all I and j, and this is also the skew product, so we have to write it as the sum over I lower than j d j lower than I dfi dxj minus dfj dxi, and here dxj dxi. So this is called a differential of a one form, and it is an expression also with two differential, which we will call two forms. Let us see that this differential operator has the very important properties. It is an involution. So d square is equal to 0. It means that if you take the one form lambda produced from a function, its differential will be 0. Okay? So differential of df, what is it? It is differential of the sum of fi dxi, and it is the sum over j less than I. I'm sorry. Here it is df dxi, so it is equal to fi. And now it is dfi dxj minus dfj dxi, dxj, dxi. And we apply this differentiation to fi, which are partial derivatives of f. Then we obtain d square f dxi dxj minus d square of a dxj dxi dxj dxi, and it is 0 because all the summand are zeros. But we need also the definition of two forms on our variety. Omega, which is the sum I j dxi dxj. In all these cases, here fi are functions on our manifolds, and here omega ij are also some small functions on our manifold. And the differential on two forms, which will produce a three form, is defined as follows: is the sum. So here I prefer to write this way of summation: k, a. So k it's generic, and I is less than j. D omega ij over dxk, dxk, dxj, dxi, dxj. And I'd like to write it as follows: sum of k less than I less than j, d omega ij dxk minus d omega kj over dxi, and plus d omega ij dxk dxk dxi dxk dxi dxj.
So here you did just the differentiation by indices?
Yes, we differentiated all the coefficients in this expression. So we have written just the following: d omega is the sum of d omega ij as functions, okay, and then multiply by this one. But if you want to represent it in this ordered way, we should sum different derivatives.
Why derivative by k 2 times?
It is not right. It is not good. I'm sorry. Thank you very much. It is ki over j. Yes, surely. Because you see, such a term arrive in three ways. After we sum the similar terms. But I prefer to leave the formal details to the end of the course of differential geometry. Just now we can see it just in coordinate like this. Okay. I introduced all these difficult issues. to give another interpretation of the Poisson property to the Jacobi identity of a Poisson bivector. We will need only this formula of the differentiation of a two form. So let M R n is a Poisson manifold. It means that there is some bivector pi d dxi d over dxj, and we correspond to it a matrix pi 1 1 is 0, but here is pi 1 2, pi 1 n, pi 2 1 0, pi 2 n, etc. Pi n 1. We know that it is Skew-Symmetric, this matrix. But suppose let it be matrix pi. Suppose that pi is not degenerate. It means that determinant of this matrix is not 0. In this case, we can consider the matrix pi minus 1, just the inverse matrix. I will denote it issues by the matrix by the functions omega 1 2, 1 n, minus 1 1 2, omega 2 1 is also Skew-Symmetric, 0, etc. And I will define a differential form on this variety by the coefficients of this inverse matrix. Omega is the sum of omega ij dxi dxj. A statement, but maybe it will be. I will demonstrate it during the next lecture. Theorem. In this situation, when a bivector is non-degenerate, in the previous context, in this context, it means that pi is not degenerate. Pi is 0. This condition, which guarantees that the Jacobi identity fulfills.
What this rho means?
Sorry?
This rho, what does it mean?
S, Houghton bracket. You remember
Yes,
that the condition to the Poisson bivector to satisfy the Jacobi identity is equivalent to some bracket of pi with itself, which is not trivial, but exactly it guarantees the Jacobi identity. So in this context, this Jacobi identity, I have written it in the good algebraic form, is equivalent to the fact that the two form is closed. It means that the differential of this form is 0. Okay, but it is some calculation. We will start with this calculation next Monday. Now we have a break, 15 minutes, and we proceed to the seminar part of our course.